Hi everyone, welcome again. Um, Today, first we reminder some key theorem. One of the theorem reminding one a monomial ideal I is irreducible if and only if up to permutation of variables I is equal to x1 r1 and x r r. So I is irreducible if and only if I it has a this form. So to a monomial ideal I is a primary if and only if up to permutation permuting of variables I equal to x1 a1 xr ar and u1 b1 and us bs such that in here r is positive and uh, r between 1 and between 2 and n. And so in here r all I positive and r between 1 and n. And so the union of support of I1s UI contained in x1 and xr, contained in this variable x1, xr. So I is primary if and only if I has this form. So when you look the irreducible ideal, easily see that I if I is a reducible, always I is a monomial primary, but primary is not the irreducible. Why? Because if it has this element extra of the power element. So, and we can have every every primary, every irreducible ideal, every monomial monomial irreducible ideal is primary. And for if I is a monomial of degree of I less than and equal to then then ik plus 1 I this colon ideal is equal to ak is a strong persistent property for alka. And also in particular I particular uh, SL AK contain of SL AK plus 1 for all k bigger than and equal to 1. This is this theorem yesterday told about this theorem. And so we continue the subject. We start with the definition. When we look the monomial ideals, is the monomial ideals. I is monomial ideals. Are I monomials. Is a big set. So we consider a smaller set. Here, I are I polymatroid ideal. Matroidal ideal. When we look this set is less than the set of all monomial ideas. But the smallest set has some condition. With some condition, the monomial ideal has became a polymatroid ideal. So we want to define the polymatroid ideal. What is the polymatroid ideal? So definition, let I be a monomial ideal monomial ideal of R generated in single degree. In single degree means all generated all monomial generated I has the same degree equigenerated. You said the equigenerated ideals same all monomial generated I has the same degree. The degree of all of the generated of I is equal. And satisfying, this is the first condition. And satisfying in the following condition. In the following conditions. For all monomials U and V belong to GAA with degree of U over xi bigger than degree of V over xi for all monomial uv, degree of u or xi bigger than this, there exists j between 1 and n such that degree of v, the converse of this one, v over xg bigger than degree of u over xg. And xj multiple u divided xi belong to GA. What is the degree of omega over xi when omega is equal to x1 r1 xn rn? Degree of omega over xi is equal to to ri. The power of xi is the degree. The power of xi is degree of xi. So for the polymatroid ideal, we have two conditions. The first condition, single degree. The second condition, for all monomial ideal, monomial U and V in GA, minimal generated. With this condition, there exists this condition. So this element belong to GA. For examples, let I equal xz, xy, and zy. Then I is polymatroid. Why? Because check the generated. His name U1, name U2. Put the name of XY U2. Put the name of ZY is V3. And so V1 and V2, all of the same degree. Degree is 2. Degree of the all of generated is the same. And this one, degree of U1 Z is equal to 1 bigger than degree of U2 Z, because the degree of this one is 0. It has not Z in here. And so must be, then there exists here, if you have this condition, we have J between 1 and n, this, and so, and degree of U2, and Y is 1 bigger than degree of U1, and Y is 0. So V1 divided Z multiple X multiple Y equal to Y XZ Z. This one is XY. Here GI. XY in GI because XY in here. And so again, for this one, U2 and U1, degree of U2 y is 1 bigger than degree of U1 x1 y and there exists degree of U1 z bigger than this is 1 bigger than degree of U2 z 0. So so z multiple U2 y equal to z, U2 equal to x y, z y equal to x xz in here. So this is the GA. And again, compare U1 and U3, U3 and U1, U2 and U3, U3 and U2. All of the generated comparing in these conditions. So by this condition, and so by continuing the same method, we conclude that I is a polymatroid, matroidal. And remark, a square free, polymatroid matroidal ideal, a square free polymatroid ideals called is called matroid ideal. Matroidal ideal. And so is square free monomial. This the matroidal. Is not the polymatroid, but the square free, so matroidal. And examples. So write the facts first. Fact. Fact. Let I be a polymatroid ideal. Let I and J be a polymatroid ideal. Ideal. Then I multiple G is polymatroid ideal. Then so writing so is IG. Then so is IG. So if I and J polymatroid, power is a polymatroid. So in particular, every power of polymatroid, matroidal, every power of polymatroidal is polymatroidal. Is polymatroidal. And examples, every power of prime ideal every power of prime ideal, monomial prime ideal, power of monomial prime ideal is polymatroid. Polymatroidal. And by this one, any product of monomial monomial prime ideal because every monomial prime ideal is matroid, and the product, any product of monomial prime ideal is polymatroid. Polymatroidal. And so another fact, let I be a polymatroid ideal. Polymatroidal ideal, then I is a normal. That is, as defined yesterday, I defined the normal ideal. That is, that here, I t integral equal to it for all t bigger than equal to 1. So all polymatroid is integrally closed. This is very good, interesting. And so by this fact, we have the following result. Ferrari, every polymatroid ideal has a strong resistant property. A strong resistance property. And so resistant property. Property. Because proof is easy. Every polymatroid matroidal ideal is normal. Is normal. Let I be a polymatroid. Matroidal, then anga a t equal to a t for all t bigger than equal to 1. And so 80 power is 1. This colon is equal to this colon ideal, t plus 1, or k plus 1, better than k. And this one, I know that this one is equal to, by theorem yesterday, I mentioned about this theorem proved by the Macadam, writing here yesterday. So this one is equal to AK hour, but this is a normal polymatroid. We have is equal to AK. So plus AK plus 1 A is equal to AK. And we know that every strength resistance has a resistance property. So other examples, the ideal I equal, let the instead of I is equal x1, x2, x3, and same on, instead of this element, write 1, 2, 3 for simplicity, for speed. And so 1, 2, 3, 1, 2, 4, 1, 2, 4 means x1, x2, x4. 1, 3, 4, 5, and 1, 4, 6, 1, 5, 6, and 2, 3, 6, 2, 3, 6, and 2, 4, 5, and 2, 5, 6, and 3, 4, 5, and 3, 4, 6. Yes, I generated by 10 elements. So this ideal satisfying in resistant property, but while I power 3, I is not equal I2. And so I doesn't satisfy in strength resistance. Why? Because x1, x2, x3, right here, 1, 2, 3, 4, 5, 6. This one belong to A3, A minus A2. When we calculate this I2, this element, multiple I belong to I3, but this element cannot here. So, so strength resistance is not old, but the resistance is old. And so this ideal is not the matroid ideal I, and I is not matroid ideal. Why? Because uh, U equal to 1, 2, 3, V equal to 3, 4, 6. So U, degree of U with respect to 1 and 2. Calculate the degree of U1 is 1 bigger than degree of V1 is 0. And degree of V, for example, 4 bigger than 1, bigger than degree of U4 is 0. So U divided 1 multiple 4, or and also because this exists, or degree of V6 1 bigger than degree of U6 0. So 4 or 6 multiple U1 is equal to 2, 3, 4. Is equal to 2, 3, 6. When we looked at here, 2, 3, 4. 2, 3, 4 is not here. And 2, 3, 6. 2, 3, 6 is not here. So it's not to GA. And this is not to G. So we conclude that I is not matroid. But this condition said that I is not matroid, because if I is a matroid, satisfy to this condition. And this condition is not hold, so I is not matroid, is not polymatroid. And also by the definitions. So
I have one question.
yeah.
Can you replace? So you ask in the persistence property, you ask that the quotient ideal by A to the k plus 1 against A is precisely I to the k, right?
Let's understand your this one.
No, in the corollary.
The corollary. Yes.
Corollary. So you have at the end this condition, right? That I k plus 1 in the quotient ideal of the last line.
Yes.
In this condition, you have that ik plus 1 against I is exactly ik, right?
Yeah, this is a colon ideal.
Exactly. So my question is this property also true replacing ordinary power by Frobenius power?
For Frobenius power, if you for Frobenius power, very special.
Yes.
Very special, but for Alka, if polymatroid for Frobenius power we have, and also if if you symbolic power,
yes,
and for symbolic power we have.
Okay.
Yeah.
Thank you.
For it's very special for Frobenius, but this one is very general. So when we for general is hold, for Frobenius power is hold. But exactly the Frobenius power of the Frobenius power of polymatroid ideal is not polymatroid.
This is interesting.
Yeah, the Frobenius power, because if we look the power, all power is polymatroid. Well, if Frobenius is not, when we looked at this one, xz, yz, and xy. The Frobenius power of this one, for example, 2. is equal to, is the Frobenius here, maybe
with brackets, with brackets.
Bracket 2, yes. This is equal to xz2, yz2, and x y2.
Correct.
This is not polymatroid. Yeah, this is one equal to x2, y2, y2, see, and this one x2, y2. It's not polymatroid.
Thank you.
Yeah. Nice. Welcome. And so polymatroid is a good example for normality. For normality, when we want to find some normal ideal, very soon go to the class of polymatroid ideal. Find many ideal has a normal conditions. And so another definition, let I be a monomial ideal monomial ideal. We say that I has linear quotient, linear quotient, linear quotients if I admit a minimal system of generated generates generators of U1 and UM such that for all I between 1 and M, one has that this colon U1 UI minus 1 colon UI is equal to U1 and UI minus 1. This is the same of regular sequence. The regular sequence has these conditions. Sorry, this is generated by for all one has this colon ideal is generated by a linear form of variables. For example, if let's take an example, use the examples. Let I is equal x to y and x to z and x z2 and y z2 and x y z. this ideal. So this ideal has a linear quotient. Uh, Example, this one, U1, U2, U3, U4, and U5. And so the first step, the eliminator of this one is 0, and U1, U2 is equal to x2, y, x, z. So this one is equal to y, and U1, U2, y3 is equal to x2y and x2z, except 2. This is equal to this one xy, and this one is x2, okay, x2, this one x2y, x2z, xz2, and yz2, yes, this one, and 0, x2y, x2z, y, and x2y, x2z, xz2. This one is divided, yes, this, okay, this one x, yes, yes, true. This one xy, and this one x, so equal to x, true. So so U1, U2, U3, U, U3, U4 equal to x to z, x to y, x to z, and xz2 colon yz2 is equal to this one equal to x2, and this one equal to x2, and this one equal to x. So this is equal x. For the if you can for the computation of this colon ideal back to the previous theorem. If you remember some theorem R1 U1 and U T, this one U, for example, U, this is the equal to summand of UI U I 1 and T. I for the computation of this colon ideal we use this equality. So another U1, U2, U3, and U4 divide U5, U5, yes, X2, Y, X2, Z, XZ2, and Y Z2 divide x, y, z is equal to, the first is equal to x, the second is equal to x, and the 3 equal to z, and so this one is equal to x, equal to x and z. So this ideal is a linear quotient because all this column ideal generated by linear form of variables is a linear form, and so on. So I is a linear quotient, has a linear quotient. Linear quotient. So for the linear quotient, order is very important. In here, the order, we consider the order U1 less than U2, V3, U4, and V5. This is the monomial order. We consider this order is a monomial order. So we want to define two interesting order in here because the polymatroid ideal has a special order. So first define, let R1 and Rn and B1 and Bn is N0N. The lexicographical order, lexicographical order, lexicographic order is the total order right with this symbol. This one, lex, under the this list under this right lex and monomials. So by sitting x power a less lex x power b, if the following condition holds, if either one sigma I 1n less than sigma bi, or if sigma I less than sigma bi, we have always x power b bigger than x power a. If sigma I and sigma b is equal, so if equal, is equal, yeah, okay, sorry, right here. If you have equal, then, or this one equal and the leftmost non-zero. The leftmost, I want to, for reverse, the leftmost non-zero component of the vector I minus b is negative. Negative. The order on R induced by the ordering we put this ordering over the variables x1 bigger than x2 xn. This is the standard ordering. The first we consider this ordering over the variables, and so define the lexicographical order. So lexicographical order is we have two conditions. If x power a less than x power b by lexi, if we have this condition is hold, we have this lexicographical order. If equal, we continue. The most non-zero component of the vector of a minus b. A minus b is a negative. Then we say that the order is a lexicographical order. And so for reverse, the lexicographical order and the reverse right here, reverse lexicographical order. Lexicographical order is the total order on mono R by this condition. In here, writing the x a lex xb, and for yes, if this condition holds, reverse lexicographical order. If we have this condition, so the monomial has a reverse equation. If equal, we have the right. Here is right. The rightmost non-zero component of the vector a minus 1 is positive. Positive. Then we said that this order is a reverse graphical order. So examples. let GA is equal to x1 power 3, x1, x2, x1, x3, 2, and x1, x3, 2, and x1, yes, x1, x2, x3, and x1, x3, power 2, x1, x1, x2, x1, 2, yes, x this one, and x1, x3, and x1, x2, 2, yes, 2, x1, 3, and x2, 3, and x2, 2, and x3, and x3, 3. So if you look this generated, all power is the equal. Is degree is 3, degree is 3, 2 plus 1 is 3, 2 plus 1, 3, and is a 1, 1, 1, 3. The degree of this monomial is 3, this monomial 3, and also. And so we don't have these conditions. So condition 2 must be checked, the condition of 2. So for Lexi, Lex x a minus 1 x3 bigger than x1 to x2, because this is r is 1, r is 2 and 0 and 2 and 1 and 0. B is 3, 0, 0. A minus b is equal to minus 1, 1, 0. It said that the right, the left hand, this is the left. The left most non-zero component of the vector is negative. The most is negative, started by negative. So x power 3 bigger than this one because this condition holds. And so x1 to x3. For this one, check. R is 2, 0, 1, 2, x2 power 0, x3 power 1. And B 2, 1, 0. This is the 0, and this one is negative. And this one is 1. The left most non-zero component is negative. Yes. This one less than this one. And so x1 x1 3, x1 yeah, x1 3, x1 x2 x2, and so this one check. 2, 0, 2, 1, 2, 0, 2, 0, 1. This 1 minus this one is negative. This is 2, and this is minus 1. The most is negative. So this one is less than this one. And also x1, x2, x3, and so right here, this one, x1, yes, this is yes, yeah. We have this number and this number, x1, 2, this one x2, and this one x1, 3. One, this one, 1, 2, yes, and x1, x1, 3, this one x1, yes, x1, x2, and x1, x3, yes, x1, x1, 2, x1, 3, x1, yes, and 2, 1, 2, 3, 1, 2, 2, yes, 1, 1, 2, 3, x1, x2, but x1, x2, 2, x1, 2, 3, x1, 3, yes, this one, and x2, 3, and x2, 2, x3, and x3, 2. Let's check. Yes. If you check this one, x2, this is a the b a here, a2, this than this one. So this one, this than this one. And so if you check this one, 2, 1, and when the here's 3, and in here x2 power 0, x2 power 0 is negative. And when we looked at here, 2, 3, 2 is 2 minus 3 is 0. And here 2 minus 1 is negative. And for reverse, we have x1 power 3, x1 2, x2, and x1 2, x3, and x1 here, x1, x2, x1, x2, here x1, x2, 2, yes, yes, and x2, 3, and here x1, 2, x3, yes, and so x1, x3 has here x1, x3, 1, yes, 1, 2, 3, and 2 power 2, 3, so 1, 3 power 2, and 3 power 3, and 2 here is remain 3 power 2, and in the end x3 power 3. When we look to this order, if look the element, x1 bigger than x2, x2 bigger than x3. If this in this element, the power of x1 bigger than the power of x1 in the 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 second element is bigger than this one. Look to this one, and also to this one. Look to x1 power 2, x1 power 2 is equal. So we go to the second element, x2. In here, x2 power 1, in here is 0. And this one is bigger than this one. And so for this, x1 power 2 bigger than x1. First, look to x1. If x1 exists, compare x1 with the second element. If x1 is not exist, we go x2. Compare x2. In here, x1 exists. So x1 is equal. Compare x2. X2 in here 1, x2 in here 0. This number, this element bigger than this element. And so in here, x1 power 2 bigger than x1. And in here, x1 equal to x1. So x2 power 2 bigger than x2 power 1. This one is bigger than this one. And so in here, x1 equal, x2 bigger than the x2. x2 in here, x2 power 0. Here 1 and here x power 0. So this bigger than this one. And so in here, x1, 1, but in here, x1, there is not exist. So first, compare x1. If x1 exists, compare x1. If x1 is not exist, compare x2. If x2 is not exist, compare x3. Oh, so for here, x1 exists 1. Here, x1, this bigger than this one. And here, x2 power 3, x2 power 3, 2. This one bigger than this one. And here, x2 power 2, x2 power 0, bigger than. This is the lex. And for reverse, look the end number, x3. If x3 is bigger in A, so this less than this one. Look the x1. Here x2, here x not x2. This one less than this one. So here x2 power 2. 2 and this one, this less than this one. This is the reverse. And here 3, 2. This less than this one. Here 3 and this x3 is 0 power 3. But this one 1. And here x3 equal and x2. x2 is 1, x2 is 0. This is bigger than this one. This is the reverse. And also look to this one. x3 is equal. This 2, it is 1. Is less than this one. And here x3 power 2 less than this one because x3 power 1. Here x1, x3 power 2 is equal, x2 1, x2 is 0. So this less than this one. And so for the end, we have. This is the reverse and lexi. So let's write my description in here. U bigger than V in the order in the lex order. In the lex order, if U has the biggest element has this condition. If U is U has more formal the beginning. The beginning, then more form of the beginning than V. And U bigger than V in reverse order if U has least form the end of the end than V. Here, if you look to here, x1, the form 1. x1, the form 1, bigger than x1, form 1. The x1 in here, power 2, in here, power 3. And for reverse, x2 bigger than x1. So this one is distant this one. Yeah. So fact, every polymatroid ideal matroid. Polymatroid is a monomial ideals. Every polymatroid ideal has linear quotient. Has linear quotient with respect to the reverse lexicographical order. Order of the generated. Generators. So we want to define the regular sequence. Definition. Let M be a finitely generated R module. A sequence y, y1 and ym in R is called a regular sequence. A regular sequence is called a regular sequence of M or M regular sequence. When M is not equal to ym and m y1 yi minus 1 m, this homomorphism is injective. This is injective. For all I 1 and M is the injective. And this number M plus yi minus 1 M is homomorphism is the form of yi M plus yi minus 1 M. So M is this sequence is set that regular sequence when we have the first condition and the second condition. This is the injective. So so like let M be a finitely generated R module finitely generated R module and I be an ideal of R such that IM is not equal to M. So if y y1 and yn ym is an M regular sequence in A I, then Y can be extended to a maximal M regular sequence in I. So note that the length of all maximal, the length of all maximal regular sequence in I equal and this and equal to dimension of M. The dimension means cruel dimension. Cruel dimension. The number of maximal the number of maximal M regular sequence M regular sequence in I is denoted by grade I M this name. And if If I is equal to maximal is denoted by depth. Depth maximal ideal cancelled. So grade M. This is the modules. Depth.
Professor Mafi, just one question.
Yes.
When you define the grade, you
Yes.
say that this length is equal to the dimension. I think it is less or equal than the dimension.
No, when the dimension is bigger than the
Exactly.
grade.
This is what I mean.
Yes.
And you say that it's less or equal. Yes, exactly.
Yeah. But
Because at some point
module is
exactly. Because at some point I listen you saying equal. No, it's less or equal. Exactly.
No, less in equal.
Less or equal, yes.
And equal happen when
you have
the module is
condition.
Cohen-Macaulay. Yes.
Exactly.
Yes. When module is a Cohen-Macaulay, that exactly is happen.
Exactly. Thank you.
Yes. And so we want to need this definition for the finding the depth of the matroid ideal. And definition, let I be a linear quotient monomial ideal. Or let I be a linear, has a linear quotient. Has a linear quotient ideal, has a linear quotient and monomial ideal. Right. Let I be a monomial ideal. Ideal has, what's that? I has linear quotients. So, and GI is equal to U1 and US. So set QI I be the number of the number of variable which is required to generator generate the colon ideal U1 and UI minus 1 UI means QI is equal to QII is equal to this number G U1 UI minus 1 UI. This is the monomial ideal. And so if you calculate the element of this ideal, this is the prime ideal because the linear quotient. We can calculate the number of variable. The number of variable is the name QI. And so, and let QI be the maximal ideal, maximal element. Qi. I 1 and S. So Qi is independent of particle choice of the ordering of variables. Generating this colloidal. This colloidal. So we want to, it has in fact, the projective dimension of I is equal to this number. This fact is proved by Herzog. Let I be a monomial. Ideal substance. I has linear quotient. Then Lensau minimal free resolution of R mod I over R is equal to Qi plus 1. That is projective dimension of Ri is equal to Qi plus 1, and so projective dimension of ideal I is equal to Qi. Yeah. This is very nice. This is for the linear quotient ideal. The projective dimension is calculate. So the minimal resolutions. So the minimal resolution of every polymatroid ideal is equal to this number, because the polymatroid ideal has a linear quotient. So, and we want to prove this theorem. Let I be a matroid ideal. Matroidal ideal of R of degree D. degree D. Matroid is a square free, and degree D, any all monomial generator of I is degree of D with support of I is equal to x1 and xn, full support. Then Qi is equal to n minus d. For the matroid ideal, the Qi is this number, n minus d. D is the generated, n is the number of variables, variable of rings. So proof. Since I is a matroid ideal, matroidal ideal, there exists there since I has a matroid ideal, then I has a linear quotient. Linear quotient, and we consider the an ordering U1 less than U2 and so on. And GI is equal to U1 and US. And colon ideal and so then I has a linear quotient, and we consider this one. Then the colon ideal U1 UI minus 1 UI is generated by a subset of x1 and xn, because I has a linear quotient. So so it is enough. It is enough to show that G U1 and this colon ideal minus 1 UI contain of x1 xn minus support of UI for all I between 1 and s minus 1. And support and G UI US minus 1 colon US, this one is equal to support equal to U1 X1 and Xn minus support of US. We want it is enough to prove this to, because if you prove this one, so the QI is the N, is the QI is the generated U. This the ideal is a matroid ideal degree D. The degree of all generated is degree. This degree is D, and this set minus this set. This set has a N element. This set has a D element, and N minus D. So we have the QI. We want to prove this one. So write UI is equal to xi1 and xid if xit belong to u1 ui minus 1 ui for all t less than and d. We want to that this condition, this assumption is not happen. Xi, if here this colon ideal for t less than d, and so then xi when t less than d, so ui has an element of this form. When t less than d, ui has an element of this form. So when we xi multiple ui, this element is power 2. But in here is square free. So xi 1 and xit power 2 and xid because ui has a this form belong to u1 and ui minus 1. Let xit set here xit, one of xit here, so 2 here. So this is the xit plus 1. No, this is good. Xit. So this is a square free. And so every element belong to here is square free. And so conclude that this does not happen. So we have we have xi1, xit, xid belong to u1, s minus 1, I minus 1. Because this is a square free and only square free in here. Square free in here. So this belong to here, and this when we this belong to here, and so this is R. This one is not happen because U is not here. This is the contradiction. So this said that every this does not happen. Then so T bigger than and bigger than D. And so thus we have this condition. G U1 UI minus 1 UI contain x1 xn minus support RB. I between 1 and S minus 1. So because every element here, in here, not in here. Because if you, the element consider UI, xi, less than equal to D, we have a contradiction. And so xi with this form is not here. So containing here to set this number. And so this contain here. So now we want to prove this step. Now we show that if Y is not in support of US, then Y, variable Y, one of the X1 and Xn, Y in G U1 and US minus 1 colon US. Set US is equal to Y1, YD. Suppose UV is equal to Z1 and ZD. These two number is to GI. Such that UAS is not equal to V and Y is Y. Y in support of V and the number of support of US intersection support of V is maximal, this number. To Z, V has this condition. We may assume that Zi is equal to Yi for I, 1 and K, and ZD equal to Y, and suppose K less than and equal to D minus 2. We want to prove that this is not happen. K bigger than D minus 1. Then by definition of I is a matroid ideal. So by definition of matroid, there exists there exists I and j bigger than and equal to k plus 1 such that v multiple yi divides zi zj this one belong to g1 gi, which is a contradiction. Because when we have this element in gi, and so this condition, the number of elements divide to zj, j is not equal to here zi and to zi to zk is equal to y1 to yk, and this one zj. If you from v zj cancelled and added y to z to v, then v and us has a number bigger than this set. But this is the assumptions. V is the choose the V is the biggest number in this condition, and so finding one element bigger than this one, and so this is the contradiction with this condition, and so this does not happen. So K bigger than this one. K is equal to, and so K is equal to D minus 1. D minus 1, and so Y US divide YI belong to GI, and therefore Y in G U1 and US minus 1 and US. So this here, and so this belong to here because the GI I is generated by U1. This is the YS, and so YUS belong to divide by G1 in here. And this is as required. So, and so we have this complete the proof. And so we have QI is equal to N minus D. The number of this one is N minus D. And we have the query. Let I be a Monomials ideal with our degree D and support of I is equal to x1 and xn, then projective dimension Ri is equal to n minus d plus 1, and depth Ri is equal to d minus 1. Proof. Projective dimension of A is equal to projective dimension I plus 1, and so this one is n minus d as this theorem plus 1, and so projective dimension Ra is equal to n minus d plus 1. And by Oslander and Buxbaum theorem, the depth Ra is equal to n minus projective dimension of R. This is equal to projective dimension Ri is this number, and so we consider this number here, and so we have this is equal to d minus 1. The depth of Ra when I is a matroid ideal is equal to degree minus 1. Let definition, let I be a monomial ideal the arithmetic rank of A, the arithmetic of as arithmetic rank of I is defined as arithmetic rank. I is equal to minimum t in n such that the radical of u a1 at is equal to radical of I this number x1 I1, this is the monomials IR belong to R. The arithmetic rank is the minimum of this monomial such that this monomial, the radical of these two ideal is equal. So fact, height of ideal less than and equal to arithmetic rank of I. And this less than and equal to the number of generated. The number of generated of module. This is the number, minimal number of generated of I. So if I is square free, if I is square free, then height I less than and equal to projective dimension Ri is less than and equal to arithmetic rank equal and is mu I. So another fact, if I is a square free, monomial ideal of R, and D is equal to minimum degree U, such that U belong to GI, bigger than and equal to 2, then arithmetic rank of A less than and equal to n minus t plus 1. So theorem let I be a monomial ideal, matroid ideal, matroidal ideal of degree D, then arithmetic rank of A is equal to projective dimension and equal to n minus t plus 1. Proof. Projective dimension by this fact, projective dimension of RA less than and equal to arithmetic rank of A. But arithmetic rank by this fact less than and equal to n minus t plus 1. And also we have projective dimension of RA equal to n minus t plus 1. So from this projective dimension is n minus 1 and this is equal. So projective dimension of Ri is equal to arithmetic rank of I equal to n minus t plus 1. Oh. So I want to write this one here. Maybe the time is end. 2 minutes is remain. And so if you have any questions or comment, I am here. And so you can send email for me.
Just one question.
Yes.
These last results you explain about the arithmetical rank, some of them are from
arithmetic rank. Yes.
yes. Some of them are from Liubeznik, I think.
Yeah. This is the Liubeznik proved that this fact.
Exactly.
Yeah. In fact, this is the belong to the Liubeznik in 1980.
80 something.
Yes. Yeah.
Thank you.
And so thank you so much for your attention. And thank you for 4 days mini courses. I hope learn more about and study about the polymatroid ideal. This is very interesting, has a nice result. And for example, for finding the normal ideals is very easy find the normal ideals because every polymatroid ideal is normal, and also satisfy in strength resistance. And we want to say that the S step and D step is not equal in degree 3 for polymatroid ideal. For degree 2 is equal Prudy's theorem. And also for matroid ideal, S step and D step is equal in degrees 3 and degree bigger than 3, and equality is failed. So thank you so much and have a nice day. Goodbye.
Thank you for the course, Professor Mafi.
Thank
See
you.
you.
See you. Thank you. Goodbye.